So now I want to talk about the fundamental theorem of calculus in the part two. The second part of the fundamental theorem of calculus establishes the relationship between the integral and the antiderivative. Okay, and so what that means is that uh, essentially the integral is the antiderivative, right? Established at a set of bounds. All right. So let's look at the statement here. If f is continuous on a to b, then the integral from a to b of f of x dx equals f of b minus f of a, big F, right? Our statement about the antiderivative at b minus big F at a, where f is any antiderivative. Notice any antiderivative of f that is a function such that f prime equals little f. Okay, so what we're saying here is that essentially to solve or to find the integral, to find the definite integral of f of x dx, well, all we have to do is find the antiderivative of f and then evaluate it at the endpoints at a and b. And this makes doing integrals a lot easier. I mean, thank goodness for the fundamental theorem of calculus, because doing those Riemann sums and finding those limits would take an incredible amount of time. But this thing makes everything so much easier. All we've got to do is find the antiderivative. Now, that doesn't mean it's easy, but it means it's a heck of a lot easier than finding a bunch of limits. Okay, so let's take a look at how we actually use it. So let's evaluate the integral from 3 to 6 of dx over x. Now, first thing to know is that when we say evaluate the integral, we just basically mean to integrate, right? And sometimes we might just say integrate, but we're going to use the phrase evaluate the integral. And so what we're going to use is we're going to use that fundamental theorem of calculus. So first thing, I want to look that f of x is equal to 1 over x, right? Because the integral from 3 to 6 of dx over x is the same thing as 1 over x dx. So that's it. Now the antiderivative, or an antiderivative, because remember that the fundamental theorem says any antiderivative, we can use any one, so let's just use the easiest one, f of x, our antiderivative is natural log of x. So that fundamental theorem of calculus is now going to say that this thing here is going to be the natural log of x, and we write these brackets, and we write 3 to 6, and that means we're going to evaluate from 3 to 6. So this is going to be the natural log of 6 minus the natural log of 3, which is just simply equal to the natural log of 6 over 3, which equals the natural log of 2. That's it. Oh my. That is awesome. So to evaluate a definite integral here, all right, all we need to do is find what its antiderivative is, and then evaluate it at the two bounds, at the upper and lower bound. Awesome. That's great. So now let's try this one. Let's integrate from 1 to 11 the square root of 3 over z dz. Now, we're going to use some of the rules of integration to make this a little bit easier for ourselves. But first, we'll have 1 over 11, and we'll make this root 3 over root z dz. And if you remember, this is just a scalar. The square root of 3 is just a scalar, so we can actually pull that out. So now it's the square root of 3 times 1 to 11 of 1 over root z dz. Now, this thing here is the square root of 3 integral 1 to 11, and this is just z to the negative 1/2 dz. Okay? In integration, it's always easier to work with powers than work with roots, just because we have a power rule. So that's what you should do. So this is now going to be the square root of 3 times, I'm going to multiply this, and so we'll take the antiderivative of z to the negative 1/2. So this is going to be then z to the 1/2 over 1/2, evaluated from 1 to 11. So we just now are going to take that antiderivative, and at the end, we'll multiply by root 3. This is then going to equal, okay, square root of 3, just a little bit of algebra, of 2z to the 1/2 from 1 to 11. And so this will be root 3 times 2 times the square root of 11 minus 2 times the square root of 1, which equals 2 times the square root of 33 minus the 2 times the square root. So really, the thought process is pretty simple. We're just going to go out, we're going to find that antiderivative, okay? And when we find the antiderivative, All right, it's going to allow us to then evaluate that antiderivative on the bounds for the integral, and that actually allows us to figure out what our integral actually is. So let's take a look at this one. Let's say, for example, we want to integrate from 0 to b of cosine x dx. Well, we're just going to use that fundamental theorem of calculus again, so we need to know that f of x, or little f of x, is equal to cosine x. So big F of x is going to equal sine x, because that's the antiderivative of cosine. So we're going to now see that this is going to be sine x evaluated from 0 to b, okay? And that'll equal sine of b minus sine of 0, which just is simply equal to sine of b. So even though we have a variable as one of our bounds, it doesn't change the fundamental theorem of calculus. We still work with the fundamental theorem of calculus the exact same way. All right. So what's the upshot of this? Okay. When we want to integrate, and when we want to integrate with a set of bounds, we're going to use that antiderivative. The antiderivative is basically going to give us the value of the integral, and then we'll evaluate those antiderivatives at the two bounds and subtract the two. Okay. And that will give us, in fact, the value for our integral.